about 1.5, 1.7, somewhere up in there, right here. And it's integrating for 2 protons. All right, let's zoom in on that. What's that signal split into? What is it? Is it a quartet? Is it a triplet? Is it a sextet? Is it a pentet? What is it?
Pentet.
It's a pentet, right? It's got 5 lines. 1, 2, 3, 4, 5 lines, right? And so if you know it's a pentet, what does that mean? It means that the number of neighbors is what?
4.
N equals 4. N plus 1 equals 5. So let's go down to the structure and see if we can figure out which one it has 4 neighbors. What do you think? So look at all the protons. You said the purple ones?
The turquoise, the light blue.
Turquoise. Okay, got you right here. I agree with that 100%. And so we know that now we can say definitively that that signal represents the teal colored protons. I agree with that 100%. Anybody not see that? All right. What about the second one? What is that? Is that a quartet at 2 or 1.99?
Yeah.
That's a quartet, isn't it? So you expect that one to have what? How many neighbors?
3.
3. So N is 3. N plus 1 equals 4. Right? Can you spot that one down there? Which one is it?
Is it the purple pink one?
Yep. You're exactly right. You're on fire today, Taylor.
Thanks.
So it'll be the pink protons. All right. What about that triplet? What does that mean for a trip if it's a triplet? N is what?
2.
2. N plus 1 equals 3. Which one of those is a triplet?
Is it a dark blue one?
Yeah, it will have to be, right? Because that's the only set of protons that's got 2 neighbors, right? Other than the proton here, right? Well, that's not even that one. That one has 3 neighbors. I mean, let me not say that. All right, so that's the only one that has 2 neighbors. So it would have to be the blue. All right. Now we only got 2 signals left, and one of the things to interpret these spectra is you have to know where your protons show up, those chemical shifts. So these are what we call vanillic protons, right? The reason for that is that they are attached to a sp2 carbon. So you see the carbon right here in the double bond is sp2, right? So we call them vanillic protons or vinyl, right? That term, y'all heard of the material vinyl?
Yeah.
Yeah. So the vinyl is made from polymerizing ethylene, right, or double bond. So you can make vinyl from that. So that's what the term. That's why when you hear the term vanillic, it immediately brings to mind like double bonds or alkenes. All right. So here's the question: where do they show up? Well, alkene protons or vanillic protons can show up anywhere between 5 and 7. Right. So that's where they show up. Sometimes some scales you'll see 4 to 6. Some scales you'll see 5 to 7. But anywhere in that range, right? 5 to 7 parts per million. That's where those are going to show up. All right. So let's look at it. You see the integration for both is 1 hydrogen, right? Makes sense because you got 2 hydrogens here, 1 here and 1 here. But the question is, which is which, right? Let's look at the red one first. What do you think that red proton is going to be split into? How many neighbors does it have?
1.
It only has 1. That's exactly right. And so it should be a doublet, right? So the red proton is going to show up here. Now I know that seems counterintuitive because it's closer to the carbonyl than the green one, but you have to think about, like, you have to think in terms of, in like 3D, these protons are like, well, the double bond itself is flat, right? So the ring kind of looks like this. So that carbonyl doesn't have as much influence as you think, right? It's kind of pointed up this way, right? So your protons will be here, right? So it's possible that the carbonyl is more attracted to this proton, right, with that lone pair than the other one. So that may be why it's further downfield. But let's look at it. What do you expect that to be? The proton, the last proton, the green one. What do you think?
Well, it has 3 neighbors.
It's got 3
So
neighbors. So you expect it to be like
4.
a quartet or something like that, right?
Yeah.
But if we zoom on it, you'll see that it's a little bit different, right? Can you see that there is, I don't know if you can make that. I don't know how good the resolution is, but can you see that middle peak is kind of split into 2 lines? Some, you can't, I can see it, but I know the resolution is bad. But if you look at the overall signal, what you really see, right? The middle 2 lines look like a doublet, and then the outer 2 lines look like a quartet. So it's kind of like it's a complex splitting pattern, right? So it's going to actually split with this one, and it'll split with those 2, and it'll do it separately. So it's kind of another complex pattern, kind of like when we had chiral centers in place. It's along those lines. But on an exam, if you told me that it was a quartet, you would get credit, because under normal circumstances, that proton would show up as a quartet. But because it's on a pi bond, you get there's multiple non-equivalents, so it kind of screws up the splitting pattern, right? Because you can see that it's more than a quartet.
So what would we say if we weren't saying it was a quartet? Like, how would you describe it?
Well, it should be a, let me see. So you'll get a triplet for this one, and you'll get a doublet for this one. So it should be 6 lines. So it'd be either a doublet of triplets or a triplet of doublets. I need to go back and remember which one comes first. But you can see it's 6 lines, right? It's kind of 4 lines right here, and then 2 in the middle. So the total number of lines for that signal is going to be split into 6 lines. It's like it'll be n plus 1 times n plus 1. But right, so one of them be a triplet and one of them be a doublet, so it'll be 6 lines. So you either call it it's either going to be called a doublet of triplets or a triplet of doublets. And we can't see like the resolution, so I'm not sure which one it'll be. But that's another topic, right? That's really when you get into complex splitting patterns, then that's a topic for that. But I don't want to like knock anybody off the boat by going into that. I do have a video for it, but I'd rather just leave it where it is. So we're just going to keep it how it is for now. All right. Any questions about anything up to this point? Is this clicking at all for y'all? Like, I mean,
Yes.
yeah.
Mine was
All
that
right.
double triplet stuff.
Yeah. That's a different like a ball of wax, man. But it's a like the splitting patterns. You apply the same rules, but when you have what's called complex splitting, like you have systems like what we call ABX systems and AMX systems, where you have three different types of protons that split in one another, that's when you start seeing those complex splitting patterns. But I'm gonna leave that alone. I don't want to take you out too far in the deep. So, all right. So, any questions about that? Let me see if I can pull up another. Actually, let me go to Blackboard, and I'll see if I can pull up another. Let's see, because I know there's another handout on Blackboard, but for now, this is what you're going to actually physically turn in when it's time to turn in your work. And if you couldn't print it, that's fine. You can edit it digitally. I don't care, as long as you turn it in. I need to pause that too. Okay, let's look at this handout right quick. So these are three structures. I'm gonna take a screenshot of that so I can pull it back up. All right, so this will be our reference when we're looking at the spectra. So let's see if we can figure out, like, on each one of these, the number of signals. What do you think about this first one? I'm gonna have to annotate this.
Dr. Russell, we can't see anything.
Okay, sorry. All right. What about now?
Yes.
Okay, great. So let's look at this first structure here, and let me get my little pen out. What do you think? Huh?
You said this is on Blackboard?
It is. I hadn't unlocked. I only unlocked one of the NMR assignments, right?
Okay.
And it was the one that we just finished. But we can start on this, because this assignment also asks for some other information that we hadn't talked about. Like, it asks for infrared, which we haven't discussed. I mean, I can give you a crash course, but let's just see how it plays out. So first thing we want to do is figure out the number of signals for number one. What do you think?
4.
1, 2, 3, 4. I agree with that. There's no symmetry, so all of your protons are going to be non-equivalent. That texting me like 50 times, man. Sorry. So what about here? What do you think? The OH may or may not show up, depends on the resolution of your instrument, but let's say it does show up. So that's going to be 1. What about here? There's a CH2 right there, right?
Yes.
And then here there's a CH, isn't it?
Yes.
Mm-hmm. And then what about these right here? You think they're going to be on the same signal or different signals?
Same.
They're both all equivalent. All right. So if they're all equivalent, that means we should have 1, 2, 3, possibly 4. We're just talking about signals. All right. What about here? That's going to be a signal. That's going to be a signal. Is that right?
Yes.
Mm-hmm. And then you'll get a signal
That
here.
one.
So 3 signals, right? Oh, that 3 is horrible. All right. And what about up here? What do you think? So all of these, because there's no symmetry. So that's at least 4, right? And then on an aromatic ring, it's kind of hard, like, because the ring is not symmetrical, right? You expect all of these to be non-equivalent on your aromatic ring. Once you substitute that ring, it breaks up the symmetry, and so those protons usually show up as non-equivalent. We're gonna find out as we move along. All right. Any questions about that? So that should be 1, 2, 3, 4, 5, 6, 7, 8 signals. Should be 8. We'll see when we get to the spectrum. Because sometimes those